All right. Well, we'll deal without the mouse then. Wow, it's really giving me a hard time today. Ah. All right. Well. All right. Sorry for the delay there. Okay. So these are the different formulas for electrical resistance for varying cross section. There are two problems that I'm giving you in the homework. One is the resistance of a cone, which I just showed you up on the board. For that problem, you could use a formula like this to figure out the resistance. The other problem I'm giving you in the homework is the resistance of a washer, a quarter washer, quarter flat washer, annulus with an inner radius A and outer radius B, a thickness H. So for this problem, I'm just telling you beforehand that you have to use the general formula for resistance. Okay? And you have to apply a test voltage, not a test current.
Just a quick question about that particular problem.
Yes?
Is it, you want us to find the resistance in the direction the hole is in, or from one side to the other?
I can.
I mean, if it says in the
I can draw it up here. It'll look something like this.
Yeah, just making sure if it's already in the homework written, that's great. I just want to make sure there's no confusion there.
Yeah, I'll just draw what that looks like. It looks something like this. So imagine that you have a washer that looks like this and has some height to it. Okay, and you apply the voltage between here and here.
Okay.
Okay. So the inner radius is A, the outer radius is B, and then it has a thickness H. Okay. Just a quarter washer. Yeah. If you had a whole washer, then you have to have some way of applying the voltage. Now the tricky thing with this one, and I'm telling you this beforehand because it's something to think about. The reason you have to use the general resistance formula, this is a wire of constant cross section, right? What the cross section looks something like this, right? It has the width here is B minus A, and the height here is H, right? But one intuition I just want to teach you, when you have something that looks like this, where the current is going through, let's see, let me draw this in comparison. This is a very subtle but very important point. If you apply voltage to something like this, all the electric field vectors go something like this, right? Now, if you apply a voltage to something that looks like this, now your electric field vectors look something like this, right? So a subtle point about this is look at the length of this vector. This vector is shorter than the other vectors, right? So it's the same potential difference between this side and this side, but this is a shorter length vector. So where's the electric field going to be stronger?
The shorter vector.
In the shorter vector. That's correct.
Okay, so
remember, the V is equal to the negative integral of E dot dl. If this length is short, that means there's going to be a stronger electric field. If there's a stronger electric field, that means there's a stronger current density in the middle, along the inside. Can someone tell me why that is? If there's a stronger electric field, there's a stronger current density. What's the reasoning behind that?
There's more electrons moving. Well,
Yes, there's the electrons are moving faster, right?
because current is proportional to voltage.
Yeah. J is equal to sigma times E. Right, so when you have like curved, when electric fields are going around curved interfaces or curved wires, you end up getting more of a current density buildup on the inside of the wire. Larger electric fields, more current density on the inside of the wire. Okay, so that's a hint on that problem. In any case, let's continue on to some new material, okay? So today we're going to talk about electrical work and power. So we'll talk about Joule's law, and then we'll get into the behavior of fields at interfaces. Those are the two things I would like to cover today. I got this cool little animated GIF there that stopped working. I guess it only works if it's zoomed out. I want you to all understand what electrical work is. Okay, and before we understand what electrical work is, I want to remind you of what mechanical work is, because mechanical work is something that you learned in physics, in AP physics in high school, or you learned it in physics here at the university. Does anyone remember this equation? Work is equal to force times distance. Yeah? So the thing that I always like to imagine things in terms of pictures in my head. In the mechanical domain, work is when we exert a force on an object and move it through a distance. So I often think about something like this. Someone like, pulling a force or pushing a force and moving that force through a distance. Right? So in this case, the force is the weight of this thing. Where's my mouse again? It's disappeared. The force is the weight, and the distance that it's being moved through is this height, 2 meters. All right? So work is equal to force times distance, and the units for that is joules. So electrical work, I want you to think about electrical work in a very physicsy kind of way. It is also force times distance. In the mechanical domain, we're moving something that has some kind of weight to it, or some kind of force that pushes back on you. In the electrical world, the electric field is moving a charged particle. Right? So in the electrical world, you think about something like this, where you have a charge here that looks something like this, and that charge is moving through an electric field. Again, work is force through a distance. In this case, there's an electrical force exerted on that particle, and that particle is being moved. The particle moves because of that force. So it's very similar to mechanical work if you think about it. So remember that electrical force, what's the formula for electrical force? Fe equals E times Q, right? If you remember from one of the earlier lectures, we talked about FEC, right? FEQ, this is what my high school physics teacher used to say. Electric force is equal to the electric field times the charge. Right? So there's an electric field here, right? That's the electric field right there. And it's exerting a force on that charged particle. The charged particle is in the field. So the electric field is doing work on the particle. Moves it through a distance. So the electrical work is equal to force times distance, and the units is joules. But now the force is equal to E times Q. And D is the distance. All right. So, quick problem just to get ourselves situated. Suppose we have a uniform electric field, 10 volts per centimeter. An electron is placed in the field, and due to that field, it moves 1 centimeter. How much work was done on the electron? So let's see if we can figure this out. Sorry for the noise, I'm not sure what's going on there. So, how do we solve this problem?
The field strength by the charge of an electron.
Okay. Work equals force times distance. All right, what's the force?
Q.
E times Q times the distance. All right, so the electric field is 10 volts per centimeter. Q. What is the Q? 1.6 times 10 to the negative 19 coulombs. And the distance is 1 centimeter. All right. Now, for the purpose of this class, I often recommend doing everything in MKS units. Okay, but I just took a little shortcut here. You can take the shortcuts if you know that the units will cancel. So you can see the volts. I'm sorry, the centimeters here cancel, and you're left with volts volts times coulombs. A volt times coulomb is a joule. Okay, so you're left with 1.6 times 10 to the negative 18 joules of energy. That's how much energy it took to move that electron. Okay. Oops. Okay. Now, that's a very simple example. Now, in the real world, we're not really concerned about like how much work is done in moving a single charge, right? Something that's more practical for us is actually looking at a lot of moving charges. A lot of moving charges basically means current, right?
I have one question. On that last problem, we didn't put the negative sign for the charge on the electron, and I just want to make sure I'm clear about when we have positive and negative work, and theoretically.
Oh, yes. Good question. Now, the work is, so the distance that it's, okay, let's draw this. All right, let's say this is positive, and then this is,
We're assuming it moved against the field.
my computer just freeze up again. You gotta be kidding me. Oh, come on.
So should we be, can we look at it like the tendency would be for it to move against the field, so in this problem, in order to do work, it would have to be positive?
I wanted to like draw it out for you.
Okay.
I guess I'm going to be using the board more today. Let's say you have positive and negative like this. Okay, so your electric field is in this direction. So the electron is here. All right. So the electron, which direction is the electron going to move?
Actually to the left.
It'll move to the left, right? So in that case, if we do work is equal to force times distance. and the force is equal to the electric field times Q times D. Your electric field, what polarity is that going to be? If it's going from left to right. Convention generally is left to right means positive, right to left means negative. So this is going to be a positive term, and the let's see, the Q.
Q is negative.
Q is going to be negative. E times Q.
I think just in the question, it doesn't say which way it moved against or with the field. It's where.
Well, it's being moved by the field, so
It's being moved by the field.
it's going to move against the field.
The distance, the force through the distance. So the distance here, I mean, the distance doesn't have a positive or negative associated with it. So you're going to end up with a negative sign on the work.
Okay.
Okay.
Because that's its natural tendency in this.
Yes, it's kind of like a spontaneous chemical reaction.
Okay.
If you have a positive work, that means you're working against the field. You actually have to physically move it against the field.
So that should be negative movement.
Yes, it's negative work because it has a.
No, how much work was done on the electron?
Okay, gotcha.
The electric field.
So the direction is.
Yes.
Yeah,
So
how
this
much
is
work-
calculating this negative sign is calculating how much energy the electron lost when it moved.
Isn't that the absolute value of the charge?
I'm sorry?
We can always use the absolute value of the field.
You could, yes, you could use the absolute value. You just have to know what the sign is at the end. Okay, like with these types of problems, like, you know, you could end up with a positive or negative sign at the end, but you have to know how to interpret it. So a negative sign means that that it moved on its own, right? The question's asking you how much work was done on the electron. How much work did the electric field do on the electron? The electric field is pushing it in one direction, right? So if the electric field is doing the work, that means there's a positive work associated with the electric field. Okay. If, on the other hand, I was asking you how much work am I doing if I physically move this electron from here to here, then it would be negative. Okay, so I'm gonna have to, this thing doesn't work, I have to restart it again. All right, so next part here. So we're going to talk about Joule's law. I think I'm just going to leave it out of that mode because that's causing problems. So we want to generalize this to a lot of moving charges, right? We're not interested in the work in moving just a single charge. We're interested in the work being done to move a lot of charges. Okay. So that's what Joule's law is. Remember Joule's law, P equals IV. All right, ultimately, we are deriving Joule's law in this part of the class. So imagine that when current flows, there's many moving charges. So work is being done continuously. Every charge that's moving across the semiconductor, imagine that there's work being done by the electric field on it. All right, what does that exactly mean? Well, if we go back to this slide here, we're applying a potential, right? Where does that potential often come from? If we actually want to set up something like that, positive and negative potential in your lab, how do you actually do that?
You put a battery or power source across.
A battery or power source, okay? So what we're doing is now we're talking about the amount of work that the battery or power source is doing on that moving charge. Does that make sense? the power has to come from somewhere, right? We don't have the weightlifter dude. We have the power is coming from the battery or the power source. So when we're talking about this, when current flows, there are moving charges and work is being done continuously. That means the battery or the power supply is doing the work on these charges to get them to move. All right? And so when we're talking about work being done continuously, we're interested in something called power, which is the amount of work being done per unit time. So P is equal to dW over dt. Delta W over delta T. The rate of change in the work. All right, and so you'll see here that work, if you remember, work is equal to force times distance. All right, so it's force times delta x. Delta x is distance, right? So we're taking work is equal to force times delta x divided by delta t. So the delta t just came from here. It's just this dW is equal to force times delta x, the force through a distance. So when you have carriers in the material, imagine moving carriers as a result of the electric force. Oh, I forgot one very important point here. What is delta x over delta t? dx dt is velocity, right? So power, work is equal to force times distance, right? Power is equal to force times velocity. dx dt, velocity. All right? So this is going to be equal to the electric force times the velocity that the charges are moving. All right? So we're thinking from the mechanical now into the electrical domain. We're thinking about the velocity of moving charges is what determines power. So force times velocity here. All right, and we're replacing that with force, force times the velocity of the electrons plus force times the velocity of the holes. So in metals, most of the time, we're just concerned with this term. But in semiconductors, we also have to be concerned with the holes term. And that's why you have the F U electron plus F times U of H. The powers can add. You can apply the principle of superposition there. All right, so F times U E is equal to, remember, the electric force is equal to E times Q. So this force that you see here, F, is equal to E times Q. Now, where's the Q coming from? E times the charge density times the volume. I'll say it again. Force is equal to E times Q, the charge. So this is your E. This is the electric field. And the total charge is equal to the charge density, rho VE, times the volume, delta V. So we brought the delta V out here, and we have this term in this term in parentheses. And this is then equal to E times the current density due to electrons times the current density due to holes. And that simplifies to E times J. All right, so what we did here was we took the electric field out of the parentheses, and we moved the delta V in here, and that gives us Q times U. Charge times the velocity at which it's moving. Charge times velocity at which it's moving is the definition of current density. All right, this is...
See it again?
Excuse me. remember in the earlier slide we said current density is equal to charge density times the speed at which they're moving. That's the definition of current density. So what we're doing here is we're basically saying current density times the velocity at which they are moving, that's equal to J. So that's where that J comes from. Pardon me, I need to add delta V. I need to add that in there. Delta V there. And delta V here. All right. So this is the power that is the power in some volume called dV. All right, so you imagine a small chunk of wire like this. The power dissipated in that wire is equal to E times J times delta V. Now, if we generalize that a little bit more, and we want to find the power that's dissipated in a volume, let's say a wire, which may consist of many of these small little sections, then we have to integrate. The general formula for the power as an integral is the volume integral of E dot J. It derives directly from this, okay, but we're not going into all the details of how that's derived. This is the one to remember. The power is equal to the triple integral of E dot J times dV. Remember that E dot J is a scalar quantity, right? All right, so you have this is a scalar quantity, and you're integrating that scalar quantity over a volume. Another form of this, which is equivalent, E dot J, well, J is equal to sigma times E. So if you dot those two together, you get sigma times magnitude of E squared, also integrated over a volume. Okay? So I hope that sort of makes sense where, where this law came from. We're basically saying that power, power is equal to force times velocity, velocity of charges, and that force is the electric force. It's E times Q. So that's what the definition of power is. All right, now Joule's law in a wire will simplify. We take this general equation and then we look at specific cases. In the case of just a simple wire, Joule's law is going to simplify into the well-known formula P is equal to IV. So let's see how that happens. P is equal to the sigma times E squared, the triple integral of that. Now, let's look at what a wire is. Okay, in a wire, imagine that this horizontal axis is the x-axis. All right, and the current vectors are going horizontally, just as you can see here. All right, so this E is going to have just an x component. There's going to be no y component, no z component, just an x component. All right, and so this triple integral here can be broken up into an area integral and a line integral. There should be two integral signs here, just to be clear, since this is an area integral, and this has ds. Okay, so all we're doing is we're taking the triple integral and breaking it up into two different parts. This part is the integral of sigma times E, and then you still have another E here that needs to be taken care of. The integral of this first part is equal to sigma times EX times A. Why? EX is a constant. Okay, in a wire like this, the current vectors are the same everywhere. They're uniform. So if you take that integral over the entire area, it just becomes sigma times Ex times A. The second integral, we're integrating over the length of the wire. Again, the electric field is going to be constant and everywhere along the wire if you have a uniform wire. So this becomes Ex times L. And that's where this formula comes from. Sigma times Ex times A, that is the current. Remember, J is equal to sigma times E. So this thing here this part here is equal to J. This second part here is equal to so this is J times A. So this becomes I, and the second part here is the voltage. Ex times L is the voltage, and so this is IV. Does this make sense? Anything that we're not sure about? Remember, voltage is equal to the integral, the line integral of the electric field. So if the electric field is uniform everywhere, this is just going to be equal to the voltage. This integral here is equal to the voltage, the integral of E dot dl.
This specifically only works because we have because Ex is not in space, right?
Because Ex is what?
It's a constant in space. It's not.
Yes.
Yeah. You can pull it out.
The key assumption here, and thank you for emphasizing that, Isaac, is that the electric field is the same everywhere in the conductor. Under those assumptions, Joule's law simplifies into just I times V. It simplifies into the same thing that you guys have seen in your circuits classes. P equals IV is equal to I squared R is equal to V squared over R. You'll have a problem like this in your homework. Easy problem. So this is the type of problem that you'll see in your homework. 50-meter long copper wire with radius 2 centimeters. Conductivity is 5.8 times 10 to the 7th. Calculate the following. What's the resistance of the wire? What's the power dissipated in the wire when the applied voltage is 1.5 millivolts? Would you guys like to try this problem now in class just to get a little bit of practice, or do you want to just leave it for the homework?
No.
Like to try it now? Okay, great. Let's do it. All right, so copper wire, 50 meters long. Conductivity is equal to 5.8 times 10 to the 7 Siemens per meter. We're applying a voltage of 1.5 millivolts. And see if you can figure out the resistance of the wire, power dissipated in the wire, and then the applied voltage.
Is the area of the wire for pi?
I'm sorry?
What's the area of the
Oh, the area of the wire. Radius is 2 centimeters.
4 pi squared.
Yeah, area is 4 pi r squared. Pi r squared, sorry. Your radius is 2 centimeters. All right. So any any ideas? Yeah.
Really small numbers. I mean, all I was called resistance is equal to well, 1 over L over
It's
L over sigma A.
sigma A, yeah,
Mhm.
yeah, the A, which is 0.004 pi meters squared times.
That sounds about right. 6.8 times 10 to the negative 4? That sound about right?
I didn't do that.
There you go. R is equal to L over sigma A. Yeah, 6.9 times 10 to the negative 4. That's right. So L over sigma A, so 50 meters. We want to use MKS units. Sigma is given in MKS, 5.8 times 10 to the 7th. The cross-sectional area is pi times 0.02 squared, pi r squared. 6.9 times 10 to the negative 4. Questions on that? Okay. The power, quick formula for that is V squared over R. So 1.5 millivolts, 0.0015 squared, divided by the resistance, 3.3 milliwatts. So a copper wire, a big fat copper wire like that is going to have very, very little resistance. The fatter a wire is, the less resistance it has. And that's why, you know, like the wires that are designed to carry a lot of current, they have a lower resistance. So you have less power dissipation.
Are superconducting wires like really large in area?
Good question. I don't think they're necessarily really huge in area. They're just they just have a very, very low resistance.
Yeah.
They're cooled.
Superconducting usually indicates we treat the resistance as 0 or close to it because the resistance per meter is almost 0.
Right.
Or the Siemens per meter is ludicrously huge.
Right.
However you want to
Ludicrously
express
huge.
it.
Yeah, that's right. The conductivity is very, very large. Okay, so that's an easy example. So you'll have a problem like that in your homework. So now let's get into boundary conditions for electrostatic fields. All right, so there's some interesting electrostatics that occur at the interface of two materials. And so there are two general rules. So we're changing topics now a little bit. We're trying to understand what happens when an electric field goes from one medium to another, meaning it goes from, let's say it goes from a conductor to air. Let's say it goes from one dielectric to another dielectric. What happens to it? Just a reason why we're looking at this. Does anyone remember like what happens when light hits an interface?
Bends.
Reflects.
It refracts. It bends. Basically, that's correct. Why does it do that? It's because the two materials have different dielectric constants. Right. So if you look at like the classic example in physics, you shine a laser and you look at it bending between like air and water, right? It bends. So air and water have two different dielectric constants. Because of that difference in dielectric constants, that light, which is basically an electromagnetic wave, it bends. It changes the angle of incidence. So that's why we're studying this stuff. Okay, this essentially describes that phenomenon. So suppose you have an electric field. We can call that E1, and that's incident at an interface. And when we say an interface, we're talking about two different mediums that have different dielectric constants. So air has a certain dielectric, water has a different dielectric. Or air has a certain dielectric, glass has a different dielectric. So we want to know how much these angles change. So there's two rules which describe this. The tangential components, turns out that the tangential components are continuous. What do I mean by the tangential component? Well, suppose we have an electric field E1 and E2 here like this. So these two fields here. All right, if a field E1 is incident at an interface, well, it's going to have a normal component and a tangential component. This is the surface. All right, that surface has a certain angle, right? And that's described. So based on the surface, what the surface angle is, there's going to be a tangential component. The tangential component of the electric field is parallel to the surface. And E1n is the normal component. That's perpendicular to the surface. All right, so any vector can be broken up into this normal component and the tangential component. So the first rule says the tangential components are continuous. We'll look at why that is on the next slide. The second rule talks about the normal components. The normal components are the ones that are perpendicular to the interface. So E1n and E2n, the components that are orthogonal to the interface. So the relationship for that is D1n minus D2n is equal to rho sub s. So first of all, what you notice is the difference is that instead of E's, now we're talking about D's. What's the relationship between E and D? Anyone recall? Not quite. E and D are very similar to each other.
One's magnetic and one's
No. E is the electric field. What is D? Displacement field. And if you recall, D is equal to epsilon E. So D1n is going to be epsilon 1 times E1n. D2n is going to be epsilon 2 times E2n. The difference in these normal components is equal to the charge density at the interface. So let's describe what the charge density is. So imagine this is a surface, right? The interface between two different electric materials. There's a surface there, right? That surface could have charge on it. And if that surface has charge, it changes the boundary conditions. So it's described in terms of a charge density, rho sub s. All right, let's dig a little bit deeper into these rules now. So this is a a derivation for the first rule. All right, the way we derive the first rule is to use the Stokes theorem. Let's remind ourselves what the Stokes theorem is. I'm going to put this up on the board here. What is Stokes' law? Let's see. Let's jog our memories. See how much. Cross.
Circulation around the line.
Circulation around the line, right? Circulation is equal to, so going around the line. So that's a line integral E dot dl. So this is around a closed contour. We're finding the circulation of the electric field. Circulation of E field. There's two ways to find it. One is you take the line integral around a closed contour. So imagine if you have a contour like this. So this is a C. So your contour might look something like this. And you take E dot dl at every single point along that line, C. What's the other way to solve for it?
Well, the flux going out of it or through it?
Not quite. That's the divergence theorem.
Didn't each go separately?
Hmm?
Didn't each go separately?
There's a shortcut to this.
Just area.
It's the double integral of the curl. Does this look familiar? Does it evoke fear?
No.
The first one.
Boredom?
Trouble.
All right, this is another way to calculate the circulation. Now, with electric fields, for electrostatic fields, del cross E is equal to what? Let's see if anyone remembers. Electric fields are curl-free, which means del cross E is always equal to 0. That's the key. There's a key thing about electric fields. So this whole thing is equal to 0. The circulation of an electric field is always equal to 0. Right? So if you don't remember this, it's okay. This is just take this as something new. Del cross E of electrostatic fields is 0. So the circulation, E dot dl is going to be equal to 0. All right, so that's this first part here. We know that the line integral from point 1 to the same point is 0. So any type of closed contour, you take E dot dl, that circulation is going to be equal to 0. Okay, so if we evaluate this integral, we take the limit as delta H goes to 0. Let's look at what we're doing here. We'll zoom in here. So what we're doing is we are taking E dot dl along this rectangular contour. A, B, C, D, A. So we're going counterclockwise around this contour. The rule, Stokes' law says, if we finish this line integral, we do it around that contour, it has to be equal to 0. Okay? Around any contour, that line integral must be equal to 0. So what we're doing here is first we start out, we can draw a rectangle here, and this distance here is equal to delta H over 2. This is equal to delta H over 2. Delta H is just a variable that we made up. It just represents the height of that rectangle. We are going to make that rectangle as thin as possible. Okay? So we're going to make delta H go to 0. We're essentially bringing this line and this line very close together until these contours are so small that they become insignificant. But it's still a contour, right? Going around that contour still has to equal 0.
Okay.
Yeah.
You have two electric fields that are not the same. So that still holds true even if you're taking that contour through two independent, well, I guess they're not completely independent, but two different electric fields, because, you know, just using the drawing on the left there, that feels like you should be able to get like with a bend there in the center of the electric field that it's experiencing, that you should be able to get it to spin. You see what I'm saying?
Get it to spin.
Yeah. So it shouldn't.
Oh, you mean like there would be a curl
Yeah, like
associated with that?
That makes it look like it should be possible to get a curl when you're doing that cross product, as long as you have two different fields that you have to cross. And you're saying that that's not true. Why?
That's not true. Yeah.
Wouldn't that be because the fields become anti-parallel as it goes to zero? So they basically combine into one because they're both they're basically anti-parallel of each other as far as mathematically when we squeeze that 8 to 0.
No, they
So
would
even
be
if
the
there's a
same.
curve, then all the symmetry would hold no matter what that curve was. As 8 went to 0.
I mean, I think the best way to get to get to Isaac's question is just this is the second Maxwell equation.
Oh, is it just because the electric fields, like they may be two different fields, but neither of them are changing, so it's not causing any current flow?
Well, there's no in dielectric materials there's no current flow.
Oh, okay.
What we're talking about here is just how the electric field changes over the interface. So for the first thing we have to convince ourselves is this part that del cross E is always equal to 0. All right, and I think the best way to convince ourselves of that is to go back to the second Maxwell equation here and remind ourselves that in electrostatics, del cross E is always equal to 0. The original Maxwell equation is del cross E is equal to dB dot dt, dB dt. But if under static conditions,
That has to be 0.
everything is equal to 0. So if we start with that assumption, then I think this derivation, it's legit. It's in the textbook, so it's legit. So again, we are taking the integral we are going around this contour here like this, but we're making the sides of the contour, so this height, delta H, we're making delta H go to 0. So that essentially you just have this part here and this part here, and then these two sides become insignificant. So when you do that, this integral, this line integral then becomes E1 dot L1 plus E2 dot L2. So these side components basically disappear. This is similar to what we were doing with that problem with the infinitely long line, infinitely long cylinder of charge. You remember how we used Gauss's law for that? And we ignored the top and bottom caps? Because the area along the cylinder is so much greater than the area of the caps. That's what we're doing here too. So we ignore these two sides. And so E1.L, E2.L. E1.L, based on, like you can see here, the electric field is going in this direction, in the negative direction. L is going in this direction. This dotted with this is negative. The electric field here is going in the left to right direction, so the electric field here, the tangential component here, is positive. So when we dot the electric field with this vector, okay, this vector here is tangential to the surface. So whenever you take this vector and you dot it with the tangential vector, you're getting the component of the electric field on that tangent vector. So that's why you get E1t here. Similarly, you get E2t here. All right, and this equation basically tells you that E1t is equal to E2t. The tangential components are equal. Or it is, saying it in a different way, the tangential components are continuous across the interface. Does this make sense how I got that? Sort of. Okay, the second rule. The second rule is D1 minus D2 is equal to rho sub S. Now to derive that, we are going to use Gauss's law. All right, so the first thing that we derived was from Stokes' law. This one is Gauss. So let's write down Gauss's law or the divergence theorem. So we use a Stokes theorem to calculate circulation. What do we use the divergence theorem to calculate?
Further flux.
Yeah. Flux is equal to integral of E dot ds, which is also equal to what? Volume integral of del dot E. Okay? So this is just a reminder, just so you know, always good to bring up some old trivia. That's the divergence theorem. Gauss's law says that this is equal to, what is Gauss's law? E dot ds equals what?
E times surface area equals Q over epsilon.
Q over epsilon, that's correct. Let's remind ourselves what Gauss's law means. The double integral of E dot ds, imagine that as like a surface, okay? Like some kind of sphere or some other like closed surface. That's E dot ds. Q over epsilon is the charge contained in that surface. Right, so make sure you visualize that. Just picture some kind of closed surface like this, and that surface contains some kind of charge Q. So that's the Q here. Epsilon is the dielectric constant, and E dot ds is the integral of the electric field around the surface. All right. So now that we've reminded ourselves of that, we can derive the rule 2. This is Gauss's law. Q is equal to D dot ds. Remember Q over epsilon, if we just move the epsilon to the other side, then the E becomes D. So that's this is basically Gauss's law. Q is equal to the integral of D dot ds. All right. Now, we're going to use a Gaussian surface. We'll choose a cylindrical surface. All right. Imagine the cylinder going extending across the interface. And you have the top half here, the bottom half here, and then you have the height of the cylinder, which has a height h. We're going to do the same thing again. This time we're going to smash the cylinder. We're going to make this delta h go to 0, just like before. Except this time we're using Gauss's law instead of Stokes' theorem. When we do that, this part of the integral is going to disappear. So we can ignore the cylindrical surface, this outside here, and we're just going to account for the top and the bottom cap. All right, so this Q is equal to D dot ds. Instead of having 3 different surfaces to integrate, we only have 2. We only have to consider the top surface and the bottom surface here. So this is the top surface, and then this is the bottom surface. So Q is then equal to D1 times N2. All right, notice that D1 and N2 are both pointed upwards. Right, ds is always pointed away from the inside. It points from inside out. So N1 is pointing out, N2 is pointing out. D2 is pointing in, D1 is pointing out. Now, the reason for that is just how the electric fields, how we've defined them. E1 is going away from the interface, E2 is going towards the interface. All right, so Q is equal to D1 times N2 hat. and plus d2 times n1 hat. We're basically summing up the surface integral on the top and the surface integral on the bottom. All right, and then ds is the surface area of the top cylinder or the bottom cylinder. They both have the same area. All right, so this becomes rho s times delta s. Rho s is the surface charge density times the area of this circle here is equal to d1 minus d2 times the area of the circle here. All right, this q, we just basically said the total charge q is equal to the surface charge density times the area. All right, you can take out the delta s on both sides, and you're left with rho sub s is equal to d1 minus d2n, d1n minus d2n. All right, so I would like to do an example problem for this in the last 10 minutes of class. And I think I'd like to do this problem because this is the more complicated problem. Okay, since my pen isn't working, I'm just going to do the problem on the board, and I'm going to walk you all through it. If we have time, we'll come back to this first example here. So I have this in my notes here, so let me just pull it out. All right. So I can go through this quickly since I have. Is my pen? Okay if I erase this? All right. So this is the most general problem I can give you for boundaries, types of problems on boundaries. I'll go over here. Okay. So the problem is you're given an electric field, E1, and it's incident on a surface with normal vector 1, 1, 1. There's a lot of things we have to consider in this problem. So let's consider that we have some kind of arbitrary surface like this in three-dimensional space, and that surface is defined by the surface normal vector 1, 1, 1. So this vector here is 1, 1, 1. Okay. Now we have an electric field 2, 3, 4 that's incident on the surface. So let's say something that looks like this.
So what's the question for the problem?
I'm sorry?
What's the question?
The question is, you're given an electric field. Let me explain that. This is E1. This E1 is incident on the interface. You're asked to calculate E2. So E2 is this vector here. Okay? So we know that, when E1 goes into the surface here, or goes into this interface, let me redraw that. It's going to bend. And we want to figure out how much it's going to bend. I'm not doing a great job. Let me draw this in 2D, because I think it'll be easier to see. So the surface normal vector here is 1, 1, 1. So let's assume that you have E1 going in here, and you have E2, something like this. So one little point that I want to make here, and you could jot this down, this is something good to remember. If you're going from a medium of lower dielectric constant to higher dielectric constant, the electric field will actually bend towards this normal. So these are the angles of incidences. So epsilon 1, this first medium, is equal to 1. The second medium, epsilon 2, is equal to 3. So we're going from a low dielectric medium to a higher dielectric material. In this case, the electric field will actually bend towards the normal. We're actually going to calculate the angle of incidence, and we can do that in the next 5 minutes. So let me quickly walk you through the steps of how to do this very general problem. So you're going to calculate E2 and the two incident angles. Assume that the dielectric constant here is 3, the dielectric constant at the bottom is 1, and the interface is charge-free. Okay, so let's start here. The first step that you want to do. The first step in the problem is to figure out n hat. Well, let me just put it another way. The first thing you want to figure out, I'll label this. Find the normal and tangential components of E1. So we want to do E1N and E1T. So we're going to find out these two components. Why are we doing this? Remember, we have these two rules, right? E1T is equal to E2T. D1N is minus D2N is equal to rho sub S. So we're going to use those rules to figure out the electric field on the other side of the interface. That's the strategy. Okay. So E1N is equal to E1 dotted with n hat times n hat. Where is this random formula coming from? I'm going to bring you back to one of the slides that we showed earlier.
In projection of E across n or onto n.
It's a projection of E on n. Very good. So this is a slide, I recopied this slide in this part of the presentation as well. This is when we were doing vector math. If you have an arbitrary surface that has a surface normal vector n hat, and then you have an arbitrary vector E, if you want to find the tangential and normal components, this is how you do it. The normal component, which we're finding out right now, is a projection of E on n hat. And n hat is the surface normal vector in the unit vector in that direction. So we have to figure out the unit vector. So this is equal to the component of E on n hat times n hat. And this is equal to E dot n hat times n hat. It's those cross products coming back. All right, so we'll go through this quickly. First of all, if we want to calculate n hat is just equal to n divided by the magnitude of n. All right, so we won't belabor that. That's 1, 1, 1 divided by the square root of 3. So that's n hat. All right, so E1 dot n hat is 2, 3, 4 dotted with 1 over square root of 3, 1 over square root of 3, 1 over square root of 3 times n hat. All right, so this becomes 2 plus 3 plus 4 over square root of 3 times n hat, which is 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. All right, this is all just plain old vector map. Nothing too exciting going on here. All right, so this becomes 9 divided by square root of 3. So this is a scalar multiplied by this vector. And when you multiply that out, you get 3, 3, 3. All right, so what we found here, this is the if this is E1 and this is the interface, E1 can be broken up into two components. We draw a right triangle here like this. This is E1n. This is the normal component. All right, so that vector looks like this. This is E1. And then the tangential component is the other part. Okay? So this is E1. We've broken it up into the normal component and the tangential component. We just figured out what the normal component was. Does anyone know a quick way to find the tangential component? Well, it's up on the board. It's up on the thing.
Yeah, it's the original vector minus the normal.
Right. E is equal to the tangential component plus the normal component. All right, so if we know E and we know the tangential, then we know the normal component, then ET is just equal to E minus EN. All right, so second step here. Oh, okay, we're already over. I will speed it up a little bit just so we can finish this example. So the tangential component, E1t. So E1t is equal to E minus E1n. And without showing you all the math, this is just negative 1, 0, 1. So it's 2, 3, 4 minus 3, 3, 3. All right, so we figured out the tangential, the normal and tangential components. The second step is to find the normal and tangential components of E2. So in other words, we want to find E2t and E2n. All right, what's E2t?
Negative 1, 0, 1.
E2t is equal to E1t, right? That was the property that we found. The tangential components are continuous. So E2t is equal to E1t, and so that is negative 1, 0, 1. All right, now how do we find E2n? All right, so we have to use the second identity, D2n minus D1n is equal to rho sub s. Now in this problem that we were given, notice that it says the interface is charge-free. So what is our rho s then in this problem? Okay, so rho s is equal to 0 here. So D2n equals D1n. All right, and if we add in the epsilon 1 E2n, I'm sorry, epsilon 2 E2n is equal to epsilon 1 E1n. All right, because remember, D is equal to epsilon E. All right, so E2n is equal to epsilon 1 over epsilon 2 E1n. And this comes out to 1/3 times 3, 3, 3. This is 1, 1, 1. All right, because we're given E1 is equal to 1, E2 is equal to 3. So that's where this 1/3 came from. E1n we figured out in the first problem, the first part of the problem, 3, 3, 3. Multiply the two together, so we have E2n is equal to 1, 1, 1. So now that we found that, we can find E2. So E2 is equal to E2n plus E2t. So we add these two vectors that we found together. This is E2t and this is E2n. So it's 0, 1, 2. All right, so we found the electric field on the other side of the interface. Any questions about how to do that? Okay. One last part before I let you go. We're just going to calculate one of the incident angles, not both of them, just in the interest of time. Find incident angle. All right, so what we're going to solve for here is this. What is alpha 1? The angle between E1 and the surface normal vector. How do we find that?
Cosine inverse of E1 over E1n.
Close. There is an inverse cosine in there.
Or E1n over E1.
Or you're saying just find it using this triangle? Yeah, that could work too. Yeah, that could work. So you're saying inverse what?
Cosine of E1n over E1.
Yeah, inverse cosine of E1n over E1, but we have to do it with the magnitudes. There's two ways to solve this problem, right? Alpha 1 is equal to the inverse cosine of, what is it?
E1n over E1.
E1n over E1, right? So remember, we have to do the magnitudes here. Remember, E1n and E1, they're vectors, right? But if we just want to apply Pythagorean theorem here, we have to find the magnitudes of them. All right? Yeah. So that's one way to find it. And the other way to find it is by using cross products, or dot products, if you remember. So remember this relationship. This will work. In fact, this is a quick calculation. So that's a good way to find it. But just I want to remind you that E1 dotted with n is equal to the magnitude of E times the magnitude of n times the cosine of theta, or cosine of the angle between the two. So that's cosine of alpha 1. Remember from the definition of dot products. Dot products can be used to find the angle between two vectors. So we want to find the angle between E1 and n. So we use the dot product of E1 and n. E1 dotted with n is equal to the magnitude of E, magnitude of n, times the cosine of the angle separating them. All right, if you solve this for alpha 1 is equal to the inverse cosine of E1 dot n divided by the magnitude of E times the magnitude of n. All right, and since the math here is very, very, very straightforward, I'm not going to go through it, but you will end up getting about 15 degrees here. All right, 15 degrees for alpha 1. Alpha 2 is equal to about 39 degrees. That's what I found. Okay, questions on this type of problem? This is one of those, it's like kind of a long problem, but not a difficult problem. Okay. Thanks everyone for your attention and for staying a little bit extra today. Homework will be posted, so again, make sure that you turn your homework in. If you do work on it over the weekend, it's a great idea because then you can bring questions on Monday, and I can help answer those questions. All right.